Imagine, right, intentionally injecting antimatter into a living human brain. It sounds like pure science fiction or, maybe a highly questionable plot from some mid-century comic book.
Oh, absolutely. It does.
But this isn't fiction. This collision of quantum physics and neurobiology is, it's happening every single day in psychiatric research. We are actually harnessing the annihilation of antimatter to illuminate the darkest, most elusive corners of the human mind.
It is a profound concept to wrap one's head around, isn't it? I mean, we are using fundamental physical realities, the decay of unstable isotopes, to answer these incredibly nuanced questions about human emotion, cognition, and, well, suffering.
And that is exactly why we are plunging into this material today for our deep dive. Usually, when we discuss a medical diagnosis, there is a comforting expectation of visible precision. You fracture your tibia, the x-ray reveals a jagged white line on a black background, and the orthopedic surgeon points at it and says, there is the problem.
Right. It is structurally obvious. We naturally gravitate toward that kind of certainty. We prefer our pathology to be neatly categorized in physical, three-dimensional space. A tumor, a lesion, a fracture.
Spot on. But then you cross the threshold into the world of psychiatry and neurodevelopment, and suddenly that x-ray machine is, it's utterly useless.
Completely useless.
We are looking at a diagnostic landscape that is entirely murky.
Right.
We are dealing with phenomenological symptoms, complex behaviors, and deeply subjective experiences. A patient comes in with severe depression or acute psychosis, and if you put them in an MRI scanner, their brain usually looks perfectly intact.
Hardware appears flawless.
Exactly. Which sets the stage for today. We are immersing ourselves in Chapter 1.27 of Kaplan and Sadok's comprehensive textbook of psychiatry. Our focus is radiotracer imaging, specifically positron emission tomography, PET, and single photon emission computed tomography, SPECT. Our overarching mission here is to move beyond those static structural images of the brain and understand how we can actually visualize the neurochemical engines that drive thought, mood, and behavior.
And which brings us to a fundamental definition that we really must establish before we go any further. Psychiatry, at its absolute core, is the study of how brain, mind, and experience interact, and critically, how that process can go wrong.
How it goes wrong, right?
Yes, structural imaging, like that beautiful high-resolution MRI you mentioned, gives us a highly detailed picture of the anatomical hardware. But psychiatric illnesses are very rarely hardware problems in a gross structural sense. They are chemical problems. They are dynamic, fluctuating software problems.
So if our goal is to truly understand how the brain, mind, and experience interact, we have to use tools capable of capturing that interaction in real time within the living human brain.
Precisely.
To give us a mental anchor for this, let's think about it this way. If an MRI is a highly detailed satellite map of a city's streets, showing you every avenue, every bridge, and the exact dimensions of every building,
which is incredibly useful for navigation, of course.
Right, very useful. And an EEG is simply the ambient sound of the traffic noise echoing up from those streets. Radiotracer imaging is an entirely different paradigm. It is like attaching a highly specific GPS tracker to one particular fleet of delivery vans. It allows us to watch the actual chemical messengers driving through the living brain, navigating the traffic, and parking at their designated destinations.
That is a brilliant way to conceptualize the shift in perspective. We are no longer looking at the streets. We are explicitly tracking the cargo. We are tracking specific biologic processes in vivo.
Yeah.
We are isolating neurotransmitter systems, quantifying receptor availability, and measuring cellular metabolism as it actually happens.
Okay, let's unpack this, because before we can talk about how this illuminates schizophrenia or depression or target engagement for new medications, we have to deal with the sheer mechanical physics of it all.
The maths and the physics, yes.
Right. How can we possibly see a single molecule or a specific fleet of molecules operating deep inside a living human skull?
Well, the foundational concept we have to master is the tracer. And interestingly, this idea predates modern neuroimaging by quite a few decades. We owe this to George de Hevesy, a Hungarian radiochemist.
Back in the mid-20th century, right?
Yes, back in the early to mid-20th century, long before we had computers capable of tomographic reconstruction. De Hevesy pioneered the use of radioactive isotopes incorporated into biological systems. He actually won the Nobel Prize in Chemistry in 1943 for this work.
Oh, wow, 1943.
Yeah. He realized that if you label a molecule with a radioactive isotope, you can follow its path through a living plant or animal by detecting the radiation it emits.
He essentially invented the concept of biological espionage. You slip a tracking device onto a natural molecule and watch where it goes.
That's a good way to put it.
But my immediate concern, and I imagine the concern of anyone thinking about injecting chemicals into a brain, is the volume. If I want to study how dopamine receptors work and I flood the brain with a radioactive dopamine analog, aren't I fundamentally altering the very system I am trying to observe?
You are hitting on the most critical rule of this entire methodology right there. It is called the tracer dose approximation.
Tracer dose approximation.
Exactly. The absolute prerequisite for a radiotracer study is that the mass of the injected substance must be infinitesimally small. We are generally talking about total doses in the range of a few micrograms, sometimes even nanograms.
Just a microscopic whisper of a chemical.
Precisely. At these incredibly low mass doses, the tracer acts purely as an invisible observer. Mathematically, we aim for the tracer to occupy no more than 1%, perhaps a fraction of a percent, of the available target receptors.
So it doesn't trigger anything.
Right. At that level of occupancy, the tracer traces the system without perturbing its normal physiological or pharmacological function. The brain's regulatory mechanisms do not even register that the tracer is present.
Okay, so we inject this microscopic fleet of GPS-tagged vans. The tags themselves are the radioactive isotopes. Let's talk about the engines powering these tags, starting with PTT, Positron emission tomography.
The big one.
The big one. I brought up antimatter earlier, and I want to really dig into this because the physics happening inside a patient's head during a PET scan is genuinely staggering.
It is one of the most beautiful applications of quantum mechanics in medicine. In PET, the radioactive isotopes we attach to our tracer molecules, things like carbon-11 or fluorine-18, they have an unstable nuclear configuration.
Meaning what, exactly?
Specifically, they are proton-rich. They have too many protons to maintain atomic stability. So to reach a stable state, a proton inside the nucleus of the atom essentially transforms. It converts into a neutron, and to balance the fundamental conservation of charge, it ejects a positron.
And a positron is the antimatter twin of an electron. It has the exact same infinitesimal mass as a regular electron, but it carries a positive electrical charge instead of a negative one.
That is correct. It is true antimatter. When this positron is ejected from the atomic nucleus, it possesses kinetic energy. It shoots out and travels a very short distance through the surrounding brain tissue, usually just a millimeter or two. As it travels, it bounces off other atoms, losing its kinetic energy in a matter of nanoseconds. Once it slows down sufficiently, it encounters a regular electron in the patient's biological tissue.
And this is where the science fiction becomes reality. So it's like antimatter hitting matter, the positron hits an electron, they annihilate, and shoot out two photons in perfectly opposite directions.
That is the famous annihilation reaction, yes.
Yeah.
The particles cease to exist as matter. Their entire resting mass is converted instantly into pure energy, strictly obeying Einstein's mass-energy equivalence principle, E equals mc squared.
Wow.
And here is the crucial reality that makes PET scanners possible. That energy is released as two high-energy photons, or gamma rays. Now, because the principles of physics dictate that momentum must be conserved, and because the positron and electron were essentially at rest when they annihilated, these two photons cannot just fly off in random directions. They must shoot out in perfectly opposite directions at roughly 180 degrees to each other.
And they each carry a highly specific payload of energy. Exactly 511 kilo-electron volts, or keV.
Always 511 keV. This immutable physical law allows PET scanners to utilize a principle called coincidence detection.
Coincidence detection.
Yes. If you look at a PET scanner, it looks like a large, imposing donut. That ring is packed with radiation detectors completely surrounding the patient's head. The scanner's highly calibrated electronic circuitry is waiting for a very specific event. It is looking for two 511 keV photons striking opposite sides of the detector ring at almost the exact same instant.
When you say almost the exact same instant, how tight is that window?
We are operating in a coincidence timing window of 3 to 6 nanoseconds.
Nanoseconds.
To put that in perspective, light travels about 1 foot in a single nanosecond. If two detectors on opposite sides of the ring light up within that microscopic 6 nanosecond sliver of time, the computer system assumes those two photons originated from the exact same antimatter annihilation event.
So it draws a straight line between those two activated detectors, a line of response, or LOR.
Yes, exactly. The scanner records that an annihilation event occurred somewhere along that specific geometric line. It doesn't initially know exactly where on the line the event happened, but it knows the line itself is absolutely accurate.
Right.
Over the course of a scan, millions upon millions of these events happen, drawing millions of intersecting lines through the volume of the brain.
The elegance of that is breathtaking. We are literally using antimatter annihilation to trace geometric lines through a living mind. But what about SPECT? Single photon emission computed tomography. The acronym itself implies a totally different physical mechanism.
It is a fundamentally different approach, yeah. SPECT uses heavier radioisotopes, such as iodine-123 or technetium-99 These isotopes do not emit positrons.
So no antimatter.
No antimatter. Instead, they typically decay via a process called electron capture. An orbital electron is pulled into the unstable nucleus and combines with a proton to form a neutron. As the remaining outer electrons rapidly rearrange themselves to fill the sudden gap in the inner shell, they release energy in the form of a single characteristic X-ray photon. For iodine-123, that photon carries an energy of about 159 keV.
But wait, if the atom is just shooting out one single photon in a completely random direction, the whole mathematical trick of the PD scanner falls apart. You can't use coincidence detection. You can't draw a straight line between 2 points if you only have 1 point hitting the detector wall. So how does the scanner have any idea where that photon came from?
You have identified the primary physical limitation of SPECT straight away. Because we lack the elegance of coincidence detection, SPECT must rely on brute force physical engineering. We use collimators.
Right, the text describes these as massive blocks of lead.
Imagine a thick, incredibly heavy block of lead attached directly to the front face of the detectors. This lead block is riddled with thousands of perfectly parallel microscopic channels.
So it's like looking through a dense bundle of completely straight drinking straws.
That is an apt visual, yeah. If a photon is emitted from the brain and happens to be traveling perfectly parallel to those tiny channels, it flies straight down the straw and strikes the detector. The scanner then knows the photon must have originated somewhere along that single straight path.
But what if the photon is traveling at a slight angle?
If it is emitted at even a fraction of a degree off-axis, it enters the channel, immediately hits the interior lead wall, and is absorbed. It never reaches the detector.
That seems horribly inefficient.
Yeah.
You are throwing away an enormous amount of data. Most of the photons being emitted by your carefully synthesized tracer are just going to smash into the lead collimator and be lost forever.
It is inherently inefficient, I'm afraid. This physical filtering means SPECT has drastically lower overall sensitivity compared to PET. We capture a much, much smaller fraction of the radioactive decay events happening in the brain.
And I suppose the spatial resolution is worse too.
The spatial resolution is also generally poorer, yes. However, SPECT has historically survived and thrived for practical reasons. The scanners are much less expensive to build and maintain. They don't require the complex coincidence timing electronics. And crucially, the isotopes used in SPECT have properties that make them vastly easier to manage logistically.
Well, let's delve into that logistics issue, because when you read about the half-lives of these isotopes, you realize that radiotracer imaging is essentially a race against a ticking quantum clock. The half-lives dictate the entire workflow of the hospital or research center.
Oh, the logistics are incredibly demanding, particularly for PET. Let's examine carbon-11. From a biological perspective, carbon-11 is the dream isotope. Carbon is the backbone of all organic chemistry.
Right, it's everywhere.
If you take a complex psychiatric drug, remove a stable carbon-12 atom, and substitute in a radioactive carbon-11 atom, you generally do not alter the drug's biological, chemical, or pharmacological properties at all. It is the perfect disguise. The brain treats it exactly like the original molecule.
But the catch is the clock.
A catch is severe. Carbon-11 has a half-life of precisely 20.4 minutes.
20 minutes. Let's translate that to reality for a second. If I have a vial of carbon-11 tracer, half of the radioactive signal is completely gone, decayed into statal boron in the time it takes me to drink a cup of coffee.
Yes, and another half of what remains is gone 20 minutes after that. This means you cannot order a carbon-11 tracer from a commercial pharmacy in another state. You must have a particle accelerator, a cyclotron, physically located on the premises of your imaging center, often in the basement directly below the scanner.
You are manufacturing radioactive isotopes on demand.
You fire protons at a target gas to create the carbon-11, then you pipe that radioactive gas directly into a hot cell, which is a heavily shielded robotic chemistry lab.
Sounds intense.
It is. Your radiochemists then have an agonizingly short window, roughly 45 to 60 minutes, to synthesize the final radiotracer molecule, purify it through high-performance liquid chromatography, rigorously test a sample for sterility and pyrogens, and physically sprint the syringe down the hall to inject the patient before the signal fades away.
That is a staggering level of infrastructure. It explains why carbon-11 research is almost exclusively the domain of massive, well-funded academic medical centers. But there is a silver lining to that rapid decay, isn't there?
There is, actually. Because the radioactivity clears from the patient's system so rapidly, you can conduct multiple scans on the same individual in a single afternoon. You could scan them at baseline, administer an experimental therapy, wait an hour for the radiation to clear, and then inject them again to scan the altered state. It is invaluable for dynamic research.
Now, compare that to the other titan of PET imaging, fluorine-18.
Fluorine-18 offers a bit more breathing room. It has a half-life of roughly 110 minutes.
Almost 2 hours. That changes the business model entirely.
It does. With a nearly 2-hour half-life, you can synthesize an 18F radiotracer at a massive, centralized commercial cyclotron facility at 4 a.m. and physically drive or fly the doses to multiple imaging centers within a few hundred miles before the morning clinical schedule begins.
Much more practical.
Exactly. It also allows researchers to study much slower pharmacokinetic processes. If you have a drug that takes 3 hours to fully penetrate the brain and bind to its target, you can't use carbon-11. The signal would be gone. You need the longevity of fluorine-18.
And SPECT isotopes give you even more time, which is why they are so heavily utilized in general clinical practice.
Indeed. Iodine-123, which is heavily used in psychiatric SPECT, has a half-life of about 13.1 hours. You can synthesize it in a factory and ship it overnight via standard logistics networks across the entire country. Technetium-99 meter, the workhorse of cardiac and bone imaging, has a 6-hour half-life.
Though the textbook explicitly noted that technetium-99 meter struggles in psychiatry because it does not readily cross the blood-brain barrier.
Yes, technetium-99 meter compounds are generally too hydrophilic. They love water too much.
Ah, I see.
The blood-brain barrier is a highly selective lipid bilayer. To cross it easily, a molecule generally needs to be lipophilic or fat-loving. Iodine is significantly more lipophilic, which is why iodine-123 is the preferred isotope for central nervous system SPECT imaging.
Okay, let's trace the journey. We have our cyclotron, we have synthesized our tracer, we have injected the patient, the isotope is decaying in their brain, throwing out these invisible 511 keV photons for PET or 159 keV photons for SPECT. Now we have to actually capture those invisible flashes of energy and somehow translate them into a quantitative 3D map of human neurochemistry. So how do we get from a photon striking a machine to a clinical brain map?
The initial hurdle is transduction. High-energy gamma rays are incredibly penetrating. They pass through the patient's skull with ease, but unfortunately, they also pass right through standard electronic components. If you just put a silicon microchip next to the head, the gamma ray would ghost right through it without registering.
Just completely ignore it.
Yeah, precisely. So we have to stop the photon and force it to reveal itself. We do this using scintillating crystals.
Scintillating meaning they literally flash with light.
Exactly. The detector rings are lined with thousands of dense inorganic crystals. Materials like bismuth germanate or BGO, and more modern iterations like lutetium oxyorthosilicate, LSO.
Quite the mouthful.
Very much so. These materials are incredibly dense. When a 511 keV photon slams into one of these crystals, it is abruptly stopped. Its kinetic energy is absorbed by the crystal lattice, and a portion of that energy is immediately re-emitted and a tiny flash of lower energy photons, essentially visible or ultraviolet light.
But a tiny microscopic flash of ultraviolet light deep inside a machine doesn't give a computer a digital data point. It's too faint, surely.
It is far too faint. We have to convert that optical light into a robust electrical current, and we have to amplify it massively. For decades, the standard technology for this has been the photomultiplier tube, or PMT.
Right, PMT.
A PMT is a brilliant, almost retro piece of vacuum tube engineering. The faint light from the scintillating crystal stripes a photosensitive cathode at the front of the evacuated glass tube. The energy of the light knocks a single electron loose from the cathode.
Okay, we have transduced the signal. We have one single electron. Still not exactly a surge of power.
No, but then we use voltage to create an avalanche. That single electron is pulled violently toward a metal plate inside the tube called a dynode, which is held at a high positive voltage. When the electron slams into the dynode, the impact knocks 3 or 4 more electrons loose.
Like a bowling ball hitting pins.
Exactly. And then those 4 electrons are pulled toward a second dynode at an even higher voltage. They slam into it, knocking 16 electrons loose. Then those 16 are pulled to a third dynode. It creates a cascading, exponential avalanche of electrons.
Oh.
By the time that electron stream reaches the final anode at the end of the tube, the signal from that original single photon has been amplified millions of times into a highly measurable, distinct electrical pulse.
Though the text mentioned that these bulky vacuum tubes are slowly being phased out in favor of solid-state technology.
They are. The major limitation of PMTs is that they are highly sensitive to magnetic fields. A strong magnet will bend the path of the electrons inside the vacuum tube, ruining the avalanche. This became a massive problem when researchers wanted to build hybrid PET MRI scanners, where the PET detectors sit directly inside the massive magnetic field of an MRI.
Oh, that makes sense. The MRI would just wreck the PMTs.
Absolutely. To solve this, engineers developed solid-state silicon photomultipliers, or SiPMs, which use semiconductor microavalanches and are completely immune to magnetic interference. They are rapidly becoming the new gold standard.
So whether by vacuum tube or solid state, the scanner registers these millions of electrical pulses. In a PET scanner, it finds the coincidences and draws millions of lines of response crossing through the brain. The computer stores all this geometric line data in a vast, complex numerical array called a sinogram. But if you look at a raw sinogram, it just looks like a series of blurry, wavy lines. It doesn't look like a brain at all. How does the software rebuild a three-dimensional cortex from a massive pile of intersecting lines?
This takes us into the realm of tomographic reconstruction. And historically, there has been a significant philosophical divide in how to do this: the analytical approach versus the statistical approach. The older foundational method is an analytical algorithm called filtered back projection, or FBP.
Let me see if I have the concept of back projection right. I have a specific line of response going from the front of the head to the back, and the scanner says, exactly 100 coincidence events happen somewhere on this line.
Yeah.
Pure back projection essentially takes the number 100 and smears it evenly across every single 3D pixel, every voxel along that entire line.
Conceptually, that is exactly what it does. It assumes the radioactivity is spread evenly across the path. But when you overlay the projections from thousands of different angles, intersecting through the volume of the brain, those smeared lines begin to overlap. Where the lines intersect heavily, the numbers add up, and you build up a bright, concentrated spot of activity that corresponds to the true location of the tracer.
But if you are just smearing data endlessly, doesn't it create a blurry mess?
It does. Pure back projection creates a severe starburst effect, a massive blurring halo around any true point source of radiation. To counteract this, a mathematical spatial filter, usually a ramp filter, is applied to the raw data before it is back projected. This filter essentially sharpens the edges and suppresses the blurring halo, allowing a much clearer image to emerge.
The major advantage of filtered back projection being that it is computationally very fast. It's a straightforward mathematical operation.
It is extremely fast, which was crucial in the early days of computing. But its fatal flaw is that it is incredibly sensitive to noise. The mathematics of FBP assume that the data is perfect. It does not account for the random statistical nature of radioactive decay.
And that causes problems.
Huge problems. Because of this, FBP often produces severe visual artifacts. Specifically, it generates streak artifacts, literal dark and light streaks radiating aggressively through the image, particularly near the edges of the skull or areas of highly contrasting activity. It can make clinical interpretation very difficult.
So to get rid of the streaks, the field moved to the statistical approach. Iterative reconstruction.
Yes. The dominant modern algorithm is called ordered subset expectation maximization, or OSM. Rather than just blindly smearing the data back across the geometric lines, OSM treats image reconstruction as a massive probabilistic guessing game.
When you call it a guessing game, it sounds highly unscientific.
It is the most rigorous kind of guessing imaginable. It is based deeply on the Poisson distribution of radioactive decay.
Let's unpack the Poisson distribution. What does that mean in this context?
Think of it like predicting rain. If I tell you a storm will drop an average of 10 raindrops per square inch on a pavement, that is the average rate. But if you look at any specific square inch, one might have 12 drops, another might have 8, and a third might have exactly 10.
Okay, I follow.
Radioactive decay works the same way. We know the average rate of decay, the half-life, But the exact number of photons emitted from a specific cubic millimeter of brain tissue in a given second is a random variable that follows this Poisson probability curve.
Okay, so how does OSEM use that probability to build an image?
The computer starts with a completely arbitrary blank guess of what the brain's radioactivity distribution looks like, a uniform gray blob. It then uses complex forward projection mathematics to ask if the brain actually looked like this gray blob, and we factor in the Poisson randomness of decay, what would the raw sonogram data look like coming out of the scanner?
It creates a fake scenogram based on its guess.
Yes, and then it compares its mathematically generated fake scenogram to the actual scenogram recorded from the patient's brain.
And it spots the differences.
Precisely. It looks at the mathematical difference between the guess and reality, updates its initial image to be a little bit closer to reality, and then runs the entire massive calculation again. That is one iteration.
Right.
It repeats this iterative loop over and over, constantly refining the image until the mathematical model optimally matches the observed data.
And the resulting images from OSAM are visually stunning compared to the old method. They're smooth, the streak artifacts are completely gone, it looks much more like a real anatomical brain. But the text noted a fascinating schism here. It said that despite OSAM creating much prettier images, many hardcore quantitative neuroimaging researchers still demand to use the old, noisy, ugly, filtered back projection. Why on earth would they prefer the noisy image?
It comes down to mathematical purity versus visual appeal. OSAM, because it uses these complex statistical probabilities to smooth out the noise, can sometimes introduce a subtle mathematical bias.
A bias.
Yeah. Particularly in areas of the brain with very low levels of radioactivity, OSAM can sometimes suppress the signal too aggressively or fail to strictly preserve the linear proportionality between a highly radioactive region and a low radioactive region.
It massages the data to make it look good.
Exactly. And if you are a clinician trying to spot a tumor, OSAM is perfect. You want a clean image. But if you are a researcher who cares deeply about extracting an exact, absolute numerical parameter, say, you need to calculate receptor density down to the third decimal place to prove your experimental hypothesis, that slight statistical bias introduced by OSAM is unacceptable.
I see.
You will choose the ugly, noisy FBP image every time because while the noise is heavy, it is at least mathematically linear and predictable.
That tension between the aesthetic image and the mathematical truth is fascinating. Now, before we can even run those reconstruction algorithms, we have to deal with the physical obstacles the photons face. Because the brain isn't floating in a vacuum. It is a dense organ, surrounded by a cerebrospinal fluid, encased in a thick bony skull, wrapped in muscle and scalp. What actually happens when a photon tries to blast its way out of the head?
This introduces the massive problem of attenuation and scatter. When 511 keV gamma rays pass through biologic tissue and bone, they don't always travel in a perfectly straight, unimpeded line. The vast majority of interactions they have with the tissue result in what is called Compton scattering.
Walk me through Compton scattering.
Imagine throwing a rubber bouncy ball through a dense forest. If you throw it, there's a high probability it will strike the trunk of a tree. In Compton scattering, the gamma photon strikes an electron in the patient's tissue. It transfers some of its kinetic energy to the electron, knocking the electron out of its orbit, and in doing so, the photon is deflected off its original path. It changes direction and loses energy.
But the scanner only knows how to draw straight lines. If a photon is deflected, the scanner will draw a line based on its new trajectory, which means it will place the radioactive event in completely the wrong part of the brain.
Exactly. That is scatter. But an even bigger problem is attenuation, when the photon is deflected so much or absorbed entirely that it never reaches the detector ring at all. Now imagine a tracer molecule sitting in the dead center of the brain, deep in the thalamus. When it emits a photon, that photon has to travel through 10 centimeters of dense brain tissue and bone to escape. It has a very high probability of being attenuated.
Whereas a molecule sitting right on the surface of the cortex, just a few millimeters from the skull, has an easy escape route.
Precisely. If we do not mathematically correct for this physical reality, the resulting image will be horribly distorted. The center of the brain will artificially look incredibly dark, as if there is no tracer there at all, simply because all the photons originating there were absorbed by the skull, while the outer edges will look artificially bright.
So how do you fix it? Because you have to know exactly how much tissue the photon traveled through to correct for it.
This is where the physical properties of PET provide an almost miraculously elegant mathematical solution. Contrast this with SPECT for a moment. In SPECT, you only have one photon. The probability of that single photon surviving its journey depends entirely on exactly how deep inside the head it started. Because SPECT doesn't intrinsically know the depth, we have to make broad, sweeping mathematical assumptions, usually applying a uniform elliptical correction map that assumes the entire head is just a uniform bucket of water. It is highly imprecise.
But PET is different because of coincidence detection, the two photons.
Exactly. Remember, for PET to record an event, both 511 keV photons must make it out of the head unattenuated and strike opposite detectors simultaneously. Now let's take a specific line of response straight across the patient's head. Let's say the total distance across the skull on this line is exactly 20 centimeters. Now imagine an annihilation event happens on this line, very close to the left side, say 1 centimeter deep. The left-facing photon only has to travel 1 centimeter to escape. But its partner, traveling right, has to traverse the remaining 19 centimeters.
Okay, 1 centimeter and 19 centimeters.
Now imagine the event happens directly in the center of the brain. The left-facing photon travels 10 centimeters, and the right-facing photon travels 10 centimeters.
Okay, I follow the geometry, but how does that help?
Because attenuation is an exponential function of distance. The probability of survival is calculated using e to the power of negative mu, the attenuation coefficient, multiplied by the distance. So, for the event near the edge, the total probability of both photons surviving is e to the power of negative mu times 1, multiplied of me to the power of negative mu times 19.
Wait, let me dust off my secondary school algebra. When you multiply two exponents that have the exact same base, in this case e, you just add the powers together. So power of negative 1 plus a power of negative 19 equals negative 20.
Exactly. And for the event in the center of the brain,
That would be e to the negative 10 multiplied by e to the negative 10. You add them up, negative 10 plus negative 10 is also negative 20. The total exponent is exactly the same.
it is brilliant, isn't it? The total mathematical probability of both photons escaping depends only on the total thickness of the tissue along that specific line, completely regardless of exactly where on that line the annihilation occurred.
That is an incredibly elegant trick of physics. It doesn't matter if it happens at the edge or in the middle, the total combined obstacle course is identical.
Because of this, we don't need to guess where the event happened to correct for it. We just need to know the total physical density of the head along every single line. We do this by performing a quick transmission scan before injecting the tracer. Historically, we used a rotating radioactive rod to map the density, but today, in modern PET-CT scanners, we just take a very rapid, low-dose CT X-ray scan.
I see.
That CT scan gives us a perfect 3D density map of the skull and tissue. We feed that map into the algorithm, and it perfectly corrects the attenuation for every single LOR.
Before we move from the scanner hardware into the pharmacokinetic mathematics, we really have to pause and address the elephant in the room, which is patient safety. We have spent half an hour talking about quantum annihilation, gamma rays, and radiation. If I am a patient or a healthy research volunteer, and you sit me down and explain that you are going to inject me with radioactive isotopes, my immediate reaction is going to be alarm. What are the actual risks?
It is the most common and most important question a subject can ask. We rigorously evaluate safety in radiotracer imaging on two entirely separate fronts: radiation exposure and pharmacologic toxicity.
Let's tackle radiation exposure first.
The central governing philosophy for radiation safety in research is the linear non-threshold model.
Explain that model.
It is a highly conservative precautionary statistical model. We know definitively that massive doses of radiation, like those experienced in nuclear accidents or heavy radiotherapy, cause cellular damage and increase cancer risk. The linear non-threshold model takes that data from high exposures and draws a straight line all the way down to zero. It assumes that there is no safe threshold. It assumes that even the tiniest amount of radiation carries some microscopic non-zero risk of inducing genetic damage.
So it's a better safe than sorry approach. You assume every photon matters.
Exactly. Because of this, every new radiotracer must undergo rigorous internal dosimetry calculations before it ever touches a human. We have to figure out exactly where the radiation goes. The absorbed dose of radiation is physically measured in grays, which represents joules of energy deposited per kilogram of biological tissue. But because different tissues react differently, we weight that measurement to calculate the biologically effective dose, which is expressed in sieverts.
The textbook spends a lot of time on the concept of the critical organ. What does that mean in the context of calculating safety?
When you inject a radiotracer into the bloodstream, it doesn't just go to the brain. It circulates systematically. As the body metabolizes and attempts to excrete the foreign molecule, the radioactivity will pool in specific organs. If the tracer is highly water-soluble and clears through the renal system, it will concentrate in the urine, making the bladder wall the organ receiving the highest concentrated dose of radiation. If it is lipid-soluble and clears hepatically, it will pool in the liver or the gallbladder.
So the critical organ is whatever organ takes the heaviest beating from that specific chemical.
Precisely. And regulatory bodies like the FDA or the local ethics committees set strict, non-negotiable limits on the total allowable radiation dose per year. Crucially, that limit is not based on the whole body average. It is capped based on the absorbed dose to that single, most vulnerable, critical organ.
To put it in perspective for a listener, how much radiation are we actually talking about for a standard PT scan compared to, say, everyday life?
A standard psychiatric PT scan typically delivers an effective dose roughly equivalent to 2 or 3 years of natural background radiation from the Earth and the Sun, or perhaps equivalent to a standard CT scan of the abdomen. It is generally low enough that a research volunteer can undergo several scans in a single year without approaching the regulatory safety limits.
Okay, that covers the radiation. But what about the drug itself, the pharmacologic toxicity? If you are injecting a synthetic dopamine analog or an opioid receptor binder, are these drugs going to induce psychoactive effects? Will they make me high or nauseous or alter my heart rate?
This brings us right back to the tracer dose approximation we discussed at the beginning. By strict definition, the mass dose of the tracer is so incredibly small, again, micrograms, that it is orders of magnitude below the threshold required to induce any physiological or pharmacological effect. The receptors are bound, but in such tiny numbers that the cellular machinery doesn't trigger a systemic response.
Though in medicine, there are always exceptions to the rule.
Always. And researchers must remain vigilant. There are a few highly potent, high-affinity agonist radiotracers that are so exceptionally powerful they can induce effects even at microgram doses. A classic example is 11C-carfentanil.
Carfentanil, that was a synthetic opioid used as an elephant tranquilizer, isn't it? It's notoriously dangerous.
It is an immensely powerful mu-opioid receptor agonist. We use a radioactive version of it to image the endorphin system in the brain. Because of its staggering potency, even at strict tracer doses, 11C-carfentanil can occasionally cause transient side effects in research subjects, things like mild sedation, feelings of heaviness, or very slight hypoventilation. But these cases are the extreme exception. By and large, pharmacologic toxicity is simply not the primary concern. Meticulous radiation dosimetry is.
All right. We have navigated the physics. We have established the safety parameters. We have our beautifully reconstructed, attenuation-corrected 3D tomographic image of the brain. The scanner has done its job. But a static picture of a glowing brain is not enough to answer complex psychiatric questions. We need to transition from making pictures to extracting biological meaning. How do we interpret the changing brightness of that image over a 2-hour scan to actually measure something real, like receptor density?
Here's where it gets really interesting. This is where the true intellectual heavy lifting of radiotracer imaging occurs. We are transitioning into Section 3 of our conceptual framework, pharmacokinetic models. The maths of the mind.
I have been looking forward to this, because this is where the raw data becomes a biological narrative.
Exactly. We use mathematical constructs called compartment models. To make sense of the data, we mathematically imagine the different physical and chemical states a radiotracer can exist in as separate interacting boxes or compartments.
Okay, I want to try an analogy out on you to explain the most famous and foundational of these mathematical frameworks, the two-tissue compartment model, or 2TC.
I am all ears. Let's hear it.
Let's imagine the radiotracer circulating in the patient's arterial blood, what you call the plasma input function, is a massive convoy of cars driving rapidly down a motorway toward a huge stadium complex. That motorway is CP, the concentration in the plasma. They arrive at the stadium off-ramp and cross over into the stadium grounds. That crossing represents the blood-brain barrier.
Okay, they have entered the brain. They have entered the first tissue compartment.
Right. In the 2TC model equations, this first box is called C and D, the non-displaceable compartment. In my stadium analogy, C and D actually represents two different groups of cars. First, you have the cars that are just driving aimlessly around the stadium access roads, looking for a spot. That is the free tracer floating in the extracellular fluid. Second, you have the cars that have just aggressively pulled over and illegally parked on the grass verges. That represents non-specifically bound tracer. It has stuck to lipid membranes or proteins where it doesn't belong. It's in the brain, but it's not bound to the receptor we care about.
This is a robust analogy, and crucially, in the mathematics of the 2TC model, we assume that the cars driving aimlessly and the cars parked on the grass are swapping places, equilibrating so incredibly rapidly that we cannot distinguish between them. So we mathematically lump them together into one single compartment, CND, the non-displaceable tracer.
Exactly. Now, from that chaotic group of cars driving around, a select few find the highly secure VIP parking garage. These VIP spots are the specific neuroreceptors we are actually trying to study, say, the D2 dopamine receptors. The tracer cars pull into those strictly designated, individually numbered parking spots. That represents the second tissue compartment, CS, the specifically bound tracer.
It's an excellent analogy because it perfectly illustrates the two defining characteristics of specific receptor binding, saturability, and displaceability.
Unpack those terms in the context of the parking lot.
First, saturability. The VIP parking spots are finite. There is a maximum number of receptors, BMX. If every single VIP spot is full, no more tracer cars can park there no matter how many are driving around the lot. That is saturable specific binding.
Makes sense.
Second, displaceability. Let's say a tracer car is parked in a VIP spot, but suddenly a bigger, much more important VIP car comes along. This represents an endogenous neurotransmitter, like a massive surge of natural dopamine. That natural dopamine has a higher affinity. It can literally tow the tracer car out of the spot and take it for itself.
The tracer gets kicked back out onto the access road.
Yes, that is displaceability.
Yeah.
Now, contrast that with the cars parked on the grass, the non-specific binding. The grass is practically endless, so it never saturates. And nobody is policing the grass, so nobody is towing them. They don't follow the rules of receptor kinetics.
So we have the cars on the motorway, CP, the cars wandering or parked on the grass, CND, and the cars perfectly parked in the VIP spots, CS. But here is the major problem. The PET scanner, hovering over the head, cannot zoom in close enough to tell the difference between a car parked on the grass and a car parked in a VIP spot. It just sees the total aggregate amount of radioactivity in that region of the brain. It sees CT, the total concentration.
Exactly right. CT is simply CND plus CS. The scanner only ever gives us one number for a voxel, CT over time. The entire multi-decade history of pharmacokinetic modeling is dedicated to using differential calculus and curve-fitting algorithms to untangle that single CT number and figure out exactly how many cars are specifically parked in those VIP spots.
Which ultimately brings us to the holy grail outcome measure of almost all these studies, binding potential, specifically BPND. What exactly is it?
Binding potential, BPND, is formally defined as the ratio of specifically bound tracer to non-displaceable tracer at equilibrium. Going back to your analogy, it is the ratio of cars parked in the VIP spots to the cars wandering the lot or stuck on the grass. Mathematically, it is beautifully simple. BPND equals CS divided by CND.
But why do researchers care so deeply about that specific ratio? Why is it the gold standard?
Because physiologically, BPND maps directly onto the biology we want to measure. BPND is mathematically equal to the density of available target receptors, which we call Bayes, divided by the tracer's dissociation constant KD, which represents its affinity. Now, assuming the tracer's chemical affinity, KD, doesn't randomly change from person to person, BPND becomes directly and linearly proportional to how many receptors are physically available in that person's brain.
It is a pure signal-to-noise ratio. The cars in the VIP spots, CS, are our true biological signal. The cars wandering the grass, CND, are our background noise.
Precisely. We are measuring how powerfully the true signal rises above the background noise.
But hold on. To solve these equations, the standard two-tissue compartment model requires you to know the input function. You need to know exactly how many cars are on the motorway. To get CP, you have to insert an arterial catheter, an A line, into a patient's radial artery in their wrist. You have to draw arterial blood continuously for 2 hours, run it through a centrifuge, and pass it through a high-performance liquid chromatograph to separate the intact tracer from radioactive metabolic waste. That sounds absolutely horrific. If I am trying to run a study on volunteers with severe generalized anxiety disorder or paranoid schizophrenia, there is no way they are tolerating an arterial blood draw for 2 hours.
You are entirely correct. It is highly invasive, painful, technically excruciating, and incredibly stressful for the patient. It severely limits the kind of research you can do, which is why the development of reference tissue models in the 1990s was an absolute paradigm shift for psychiatric neuroimaging.
Okay, explain the mathematical magic of the reference tissue. How do we bypass the blood?
It relies on finding a specific region in the brain that is biologically distinct from the region you want to study. Let's say we are studying D2 dopamine receptors in the striatum. Through postmortem biology, we know that the cerebellum, the large structure at the back of the brain, is virtually completely devoid of D2 receptors. There are 0 VIP parking spots in the cerebellum.
So what happens to the tracer cars when they enter the cerebellum?
Every single car that drives into the cerebellum has no choice but to either wander aimlessly or park on the grass. Therefore, in the cerebellum, there is no CS. CS equals 0. This means that in the cerebellum, the total signal the scanner sees, CT, is exactly equal to the non-displaceable background noise, CND.
Okay, wait, let me challenge this. If we're using the cerebellum's curve as our exact measurement of the background noise, aren't we making a massive assumption? We're just mathematically subtracting the cerebellar data from the striatal data. Are we assuming that the GRAS, the nonspecific binding to lipids and proteins, is exactly the same everywhere in the brain? Isn't that a huge biological leap of faith? What if the cerebellar GRAS is structurally different from the striatal GRAS?
You have just articulated the exact criticism that keeps pharmacokinetic modelers awake at night. It is a leap of faith. It is the fundamental, foundational assumption of all reference tissue models that the volume of distribution of the non-displaceable compartment is uniform across the entire brain. And sometimes it fails spectacularly.
I can imagine.
If a patient has a condition that alters the lipid composition of their cerebellum, or if the tracer sticks to a protein that is uniquely expressed in the hindbrain, the entire mathematical house of cards collapses. Your reference tissue is corrupted, and your calculation of BPND in the striatum will be totally false.
So it is a calculated risk. But when it works, it allows you to calculate receptor density without ever drawing a drop of arterial blood.
Yes. It opened the door to scanning massive cohorts of psychiatric patients safely and comfortably.
Now, the 2TC model we just spent time unpacking is a reversible model. The tracer cars pull into the VIP spots, sit there for a while, and then back out and leave. But the textbook also heavily details irreversible models. Trapped tracers.
Yes, the maths diverge here. Reversible models are used almost exclusively to measure the density of structural proteins, receptors, or transporters. Irreversible models are used to measure dynamic processes, enzyme activity, or cellular metabolism. In these models, the tracer acts as a substrate for a biochemical pathway. It enters the cell, interacts with an enzyme, but it has been chemically sabotaged so that it gets trapped midway through the metabolic process.
The most famous, universally used example of this being 18-FDG, the workhorse of global PT imaging.
Absolutely. 18F fluorodeoxyglucose. It is a chemical analog of regular glucose, the primary fuel source for the brain. 18FDG crosses the blood-brain barrier exactly like glucose. Once inside the brain cell, the enzyme hexokinase grabs it and phosphorylates it, turning it into 18FDG6-phosphate.
Which is exactly what hexokinase does to regular healthy glucose to begin the process of breaking it down for ATP energy.
Precisely. But here's the trick of radiochemistry. Because the tracer has a fluorine 18 atom substituted for a normal hydroxyl group, the newly formed 18FDG6-phosphate is structurally defective. It cannot undergo the necessary next enzymatic step in the glycolysis pathway. It is stuck. Furthermore, the reverse reaction, dephosphorylation, happens so incredibly slowly in brain tissue that for the 1-hour duration of a standard PT scan, the radioactive molecule is effectively permanently trapped inside the cell.
It is a biochemical roach motel. The tracer checks in, gets phosphorylated by hexokinase, and it can never check out.
That is a perfect description. Because it is trapped, the curve never equilibrates and comes back down. It just goes up and up. So in our mathematical model, we don't calculate a binding potential. Instead, we calculate a parameter called kin, which is the steady-state macroscopic uptake rate constant. Kin represents the exact speed at which the tracer is being irreversibly trapped. When we apply a mathematical conversion factor, the lumped constant, to account for the slight difference in how the brain handles 18-FDG versus true glucose, we can accurately quantify the absolute rate of regional cerebral glucose metabolism.
We see a similar trapping mechanism with 18F-DOPA, don't we? To measure dopamine synthesis.
Yes. 18F-DOPA is an analog of L-DOPA. It crosses the blood-brain barrier, enters the presynaptic dopaminergic terminals, and is metabolized by the enzyme aromatic amino acid decarboxylase into 18F-labeled dopamine. Because dopamine does not readily cross the blood-brain barrier back out, the radioactive dopamine becomes trapped inside the storage vesicles and the synaptic cleft. Measuring the kin for 18F-DOPA gives us a direct, quantifiable index of how fast the brain is manufacturing presynaptic dopamine.
Which provides the absolute perfect bridge into the next phase of our discussion. We have built the immense physical machinery, we have navigated the quantum physics, we have solved the differential equations of the compartment models. Now, what do these tools actually reveal when we point them at psychiatric pathology? How has imaging changed the way we understand mental illness? Let's start with the titan of psychiatric mysteries, schizophrenia and the dopamine system.
This is perhaps the greatest triumph of radiotracer imaging in psychiatry. Historically, the entire field operated on the dopamine hypothesis of schizophrenia, which postulated a hyperactive dopamine system. But hyperactive is a deeply vague, frustratingly imprecise term. Does it mean the brain has grown too many dopamine receptors? Does it mean the neurons are manufacturing too much dopamine? Does it mean they are releasing it too erratically? Before PET, we simply couldn't know.
We were just guessing.
Yeah, exactly. Radiotracer imaging allowed us to physically dissect this system, separating the postsynaptic receptors from the presynaptic engines.
Let's talk about the postsynaptic side first, the receptors sitting on the receiving neuron. Specifically, the textbook highlights the D1 receptor debate. And reading about this, it struck me as an incredible story about the limits and blind spots of our own tools.
It is a profound cautionary tale in radiotracer development. In the late 90s and early 2000s, researchers were immensely interested in the D1 receptor, particularly in the prefrontal cortex. We knew the prefrontal cortex was vital for working memory, executive function, and cognition, areas where patients with schizophrenia show profound, debilitating deficits. To study this, radiochemists developed two major competing D1 radiotracers, 11C-NNC-112 and 11C-SCH-23390.
And different highly respected research groups use these different tracers to scan cohorts of patients with schizophrenia.
Yes, and the results were catastrophic for the field's consensus. The groups using NNC-112 published high-profile papers showing that D1 receptor availability was significantly increased in the prefrontal cortex of drug-naive patients with schizophrenia. Meanwhile, the groups using SCH-23390 published equally rigorous papers showing that D1 availability was decreased.
Completely diametrically opposite findings. I can only imagine the chaos that caused at scientific conferences. Millions of dollars in grant money, years of doctoral research, all pointing in opposite directions.
It was a massive controversy. Initially, people assumed the problem was clinical. They argued the patient populations were too heterogeneous, or that the duration of untreated psychosis was skewing the data. But eventually, a brilliant group of investigators decided to run the ultimate test. They scanned the exact same individual patients with both tracers, and the discrepancy persisted within the very same brains.
So it wasn't the patients. The patients were consistent, the tracers were lying.
Exactly. It took years of painstaking neurochemical detective work to figure out why. They eventually realized that in vivo, inside the messy, complex environment of the living human brain, both of these tracers cross-react strongly with serotonin 5-HT2A receptors. Now, when they tested these tracers in a petri dish, in vitro, they appeared perfectly selective for D1. But in the living human cortex, up to 35% of the radioactive signal they were recording was actually coming from serotonin receptors, not dopamine receptors.
Wow, the background noise was completely contaminating the signal, and they didn't even know it.
It highlights a humbling truth. In vitro selectivity does not always guarantee in vivo specificity. The different affinities these two tracers had for the serotonin receptors drove the contradictory results. We still, to this day, need better, purer D1 radiotracers to definitively answer the question of what happens to cortical dopamine receptors in schizophrenia.
Okay, so D1 is murky. What about the D2 receptor? That is the primary target for almost every antipsychotic medication on the market. If you block D2, hallucinations stop.
Mm-hmm.
So do we find an overabundance of D2 receptors in the striatum of these patients?
This was a major revelation. For decades, post-mortem autopsy studies of schizophrenic brains had consistently shown heavily elevated levels of D2 receptors. The field assumed this was the core pathology, but there is a massive confounding variable. Those patients have been taking antipsychotic medications for decades. When you blockade a receptor for years, the brain aggressively upregulates, it grows more receptors to try and overcome the blockade.
Ah, so the disease didn't cause the extra receptors, the treatment did.
Exactly. When PET and SPECT finally allowed us to look at drug-naive first-episode patients who had never touched an antipsychotic, well, we found that baseline striatal D2 receptor availability was mostly normal, perhaps very slightly elevated in some cohorts, but nowhere near enough to explain the profound, reality-breaking psychosis these patients were experiencing.
So if the receptors, the VIP parking spots, are normal in number, the problem must be the cars, the neurotransmitter itself, the presynaptic tone. How on earth did researchers use a PD scanner to prove that the brain was releasing too much dopamine?
This is where we return to your displacement analogy, where the endogenous neurotransmitter acts as the VIP towing the tracer car out of the spot. To measure release, we use highly clever dynamic experimental designs called pharmacological challenges. The most famous and illuminating of these is the amphetamine challenge.
Walk me through exactly what happens to a patient undergoing an amphetamine challenge study, step by step.
First, we bring the subject into the imaging suite and perform a standard baseline PET scan with a D2 tracer, usually 11C raclopride. We calculate their baseline BP&D. Let's say, for the sake of numbers, we find they have 100 available VIP parking spots.
Okay, baseline established.
Then, while they are still in the scanner, or shortly after, we administer a pharmacological dose of dextroamphetamine intravenously. Amphetamine enters the presynaptic dopamine terminals and wreaks havoc. It forces the dopamine transporter to run in reverse, and it breaks open the storage vesicles. It dumps massive, unphysiological amounts of stored endogenous dopamine directly into the synapse.
A tidal wave of dopamine.
Yes, this tidal wave of endogenous dopamine violently binds to the D2 receptors. We then scan the patient a second time with the radiotracer. This time, our raclopride tracer has to compete for parking spots against that massive flood of endogenous dopamine. Let's say in this post-amphetamine scan, we only find 85 available VIP spots for our tracer. We calculate the change in binding potential, the delta BP&D. In this case, a 15% drop. That drop is our proxy measurement for how much dopamine was released.
And what happens when you do this protocol in patients with schizophrenia compared to healthy controls?
The results are striking, highly replicated, and fundamentally altered our understanding of the disease. When you give amphetamine to healthy controls, you see a predictable, moderate level of tracer displacement. But when you give the exact same weight-adjusted dose of amphetamine to patients with schizophrenia, or even to prodromal patients who are just showing early signs of being at high risk for psychosis, you see significantly greater dopamine release. The delta BP&D drop is much, much larger.
Their presynaptic engines are hyperreactive.
Precisely. Their dopaminergic terminals are highly sensitized. They release far more dopamine in response to a stimulus than a healthy brain. This perfectly correlates with the positive symptoms of schizophrenia. Delusions and hallucinations are thought to be driven by this aberrant, overwhelming surge of dopamine attaching false salience to everyday stimuli.
That proves they have a hyperreactive release mechanism when stimulated. But what about their resting state? What about just sitting in a chair on a normal Tuesday? How much dopamine is sitting in their synapses at baseline?
To measure resting baseline dopamine tone, we have to flip the experiment. We have to do a depletion study. We administer an oral drug called AMPT, alpha-methylparatyrosine. AMPT is a chemical that aggressively blocks the enzyme tyrosine hydroxylase, which is the rate-limiting step in dopamine synthesis. It effectively halts the production of new dopamine.
You completely turn off the faucet.
Yes. Over the course of 48 hours of taking AMPT, the resting endogenous dopamine in the patient's synapses clears out and is not replaced. So we do a baseline scan, then 2 days of AMPT depletion, then a second scan. Because we have removed the resting dopamine that was secretly occupying some of the receptors, our radiotracer now has more VIP spots available to bind to. The BP&D goes up.
You unmask the receptors that were occupied by the baseline traffic.
Precisely. And these AMPT depletion studies definitively showed that in patients with schizophrenia, the baseline occupancy of D2 receptors by endogenous dopamine is abnormally high. It is roughly a 10 to 20% elevation over healthy controls.
So synthesizing all of this, the imaging completely refocused the field. The dopaminergic dysfunction in schizophrenia is not a postsynaptic receptor problem. It is primarily presynaptic. Too much resting dopamine tone and a violently hyperreactive release mechanism.
Exactly. It moved the entire field's focus from the receiving end of the synapse to the transmitting end.
Now let's look at the mirror image of this. Substance dependence. Because drugs of abuse, like cocaine, methamphetamine, they obviously hijack and overwhelm the dopamine system. Do we see the same hyperactive presynaptic tone in severe addiction that we see in schizophrenia?
It is deeply counterintuitive, but we see the exact opposite. Addiction presents as a neurochemical mirror image of schizophrenia.
Wait, really? Reduced dopamine in addiction?
Yes. Across a wide variety of severe addictions, cocaine, methamphetamine, alcohol, even heroin, PET imaging studies consistently show two defining features in the striatum: reduced baseline availability of D2 receptors, and severely blunted dopamine release following an amphetamine or methylphenidate challenge.
But cocaine works by blocking dopamine reuptake, explicitly flooding the brain with dopamine to create the high. Why on earth would their release capacity be blunted?
Because the brain is an adaptive homeostatic machine. chronic, long-term exposure to these massive drug-induced surges of dopamine leads to profound neuroadaptation. The brain attempts to protect itself from the flood by drastically downregulating D2 receptors and aggressively suppressing presynaptic synthesis and vesicular storage. There was a landmark non-human primate study using a tracer for VMAT2, which is the protein pump that packages dopamine into the presynaptic vesicles. That study showed that chronic cocaine administration physically reduced presynaptic vesicle availability.
The neurons are literally packing away their tools. The reward system is fundamentally depleted. It's burned out.
It is severely burned out. The dopaminergic system in chronic substance dependence is characterized by profound hypofunction, blunted resting tone, and reduced receptor availability.
Let's pause and think about the experiential implications of this for the patient, because this explains so much about the subjective reality of addiction. If your baseline dopamine tone is completely suppressed, everyday life, food, socializing, hobbies must feel incredibly gray and unrewarding.
That is the tragedy of the disease. This neurochemical blunting directly drives the crushing anhedonia, the inability to feel pleasure that recovering addicts experience. It drives the compulsive drug-seeking behavior because the individual is desperately attempting to use the drug to achieve a normal level of reward signaling in a structurally depressed system. They are no longer getting high, they are self-medicating to escape the biochemical void.
That is a stark, devastating picture of addiction. Let's shift gears from dopamine to the other massive neurotransmitter system, serotonin. Major depressive disorder and the serotonergic system. We all know that SSRIs, selective serotonin reuptake inhibitors like Prozac or Zoloft, are the frontline treatment for depression. But what do the actual PET scans show about the serotonin receptors in a depressed brain?
The serotonin system is immensely, frustratingly complex. While dopamine has a few main receptors, serotonin has over a dozen different receptor subtypes scattered throughout the brain. In depression imaging, a major focus of research has been the 5-HT1A receptor, imaged primarily with a radiotracer called 11C1300635.
The textbook noted that WA170635 is notoriously difficult to work with chemically.
It is an absolute nightmare for radiochemists and modelers. It has extremely rapid peripheral metabolism, meaning it breaks down in the blood very quickly, generating radioactive metabolites that complicate the input function. However, it remains the standard tool. Now, 5-HT1A receptors are found throughout the cortex, but crucially, they also function as autoreceptors in the dorsal raphe nuclei, which is a tiny cluster of cells in the brainstem where most of the brain's serotonin is produced.
Autoreceptors, meaning they sit on the actual neuron that is releasing the serotonin, and if they get activated by serotonin, they act as a negative feedback loop. They tell the neuron to stop firing.
Exactly. They are the brakes on the serotonin engine. In PET studies comparing patients with severe major depressive disorder to healthy matched controls, the majority of research using WY17635 has found decreased BPND, decreased availability of these 5-HT1A receptors, both in the dorsal raphe and across many cortical regions.
Though the text made a point of noting that this isn't universally accepted. There is some controversy depending on the mathematical models used.
There is a fierce methodological debate. If researchers use a specific metric called BPF, which relies heavily on calculating the precise fraction of tracer that is free, not bound proteins, in the arterial blood plasma, rather than relying on a reference tissue model, some groups actually found elevated binding in depression.
That discrepancy is wild. It highlights how fragile those mathematical assumptions can be. If there are subtle systemic differences in how depressed patients metabolize the tracer in their liver or how heavily the tracer binds to blood proteins in their plasma, it can artificially skew the brain measurements entirely.
It is a perfect example of how in radiotracer imaging, your biological conclusions are only ever as strong as the mathematical assumptions underpinning your pharmacokinetic model. It is a debate that likely requires the development of entirely new, more robust 5-HT1A tracers to finally resolve.
Since we're on serotonin, I have to ask about recreational drugs that specifically target that system, specifically ecstasy or MDMA.
MDMA is a profound, aggressive releaser of serotonin. It binds to the serotonin transporter, SERT, and forces it to run in reverse, dumping massive, unphysiological amounts of serotonin directly into the synapse. It creates the intense feelings of empathy, connection, and euphoria associated with the drug. But in the 1980s and 90s, early animal studies raised massive alarms that MDMA might be highly neurotoxic to serotonin terminals.
Were we able to visualize that damage in living human users using PET?
Yes, we were. Using a radiotracer specifically designed to bind to SERT, called 11CDSB, researchers have scanned cohorts of current and former heavy MDMA users. In this context, measuring SERT availability isn't just about the transporter. It acts as a structural proxy for measuring the physical integrity and density of the serotonin nerve terminals themselves.
And what did the scans reveal?
They consistently observed heavily reduced SERT availability, sometimes showing a 20 to 30% massive reduction, particularly in the prefrontal cortex of recently abstinent heavy MDMA users compared to matched healthy controls.
A 30% drop. Think about the human cost of that. Serotonin regulates mood, sleep, appetite. If you lose a third of your terminals, you are looking at severe, crushing emotional hollowness. Is that drop permanent brain damage? Are the neurons dead?
That is the most critical question, and the data offers some complex hope. Cross-sectional studies that included former heavy users who had been completely abstinent for long periods, months or years, suggested that the SERT levels may actually recover over time. There are strong correlations showing SERT binding levels slowly rebounding as the duration of abstinence increases. So it is highly likely that we are observing a reversible downregulation of the transporter, or perhaps a temporary pruning back of the terminal branches rather than permanent, irreversible cell death. But the acute, severe reduction in transporter availability following heavy use is an undeniable visualized reality.
Before we move into the final section on clinical reasoning, we have to spend time on the emerging frontier of psychiatric neuroimaging. Neuroinflammation, the immune system of the brain. The textbook highlighted TSPO imaging as the spearhead of this movement. What exactly is TSPO?
TSPO stands for the 18-kilodalton translocator protein. It is a protein found on the outer membrane of mitochondria. In a healthy, resting brain, it is expressed at extremely low, almost undetectable levels. However, when microglia, which are the resident macrophage immune cells of the central nervous system, become activated in response to injury, chronic stress, or active inflammation, they massively upregulate their cellular expression of TSPO. Therefore, using a radiotracer that tightly binds to TSPO allows us to essentially map activated microglia and quantify neuroinflammation in vivo.
It is a heat map for brain inflammation. But the text mentioned a massive, completely unexpected genetic hurdle that researchers slammed into when they started using the second-generation TSPO tracers, like 11C-PBR28.
Oh, it was a fascinating genetic bottleneck that nearly derailed the entire field. Researchers started injecting these new, highly refined tracers into human volunteers, and the data came back wildly, incomprehensibly inconsistent. Some subjects showed huge, beautiful signals, some showed moderate signals, and in a subset of subjects, the specific binding was virtually zero. It looked like the scan had completely failed.
Did the tracer formulation fail in the cyclotron?
No, the chemistry was perfect. The biology of the humans varied. After intense investigation, they discovered that humans possess a single nucleotide polymorphism, a tiny single-letter genetic mutation known as RS6971 in the gene that codes for the TSPO protein. This specific polymorphism physically alters the three-dimensional shape of the TSPO binding site on the mitochondria.
So the lock changes shape, and the tracer key doesn't fit anymore.
Exactly. Based on your genetics, you fall into one of three categories. You are either a high-affinity binder, a HAB, possessing two major alleles, a mixed-affinity binder, a MAB heterozygous, or a low-affinity binder, a LAB, possessing two minor alleles. If you inject a low-affinity binder with 11C-PBR28, the tracer physically cannot bind to the protein. You get almost zero specific signal, regardless of how much inflammation they actually have.
That is terrifying from a research design perspective. How do you possibly run a clinical study if the tracer arbitrarily stops working in a quarter of your patients?
You have to adapt. It forces the ultimate integration of precision medicine into research design. Today, before you can enroll a subject in a TSPO PT study, you have to draw their blood and genotype them for the RS6971 polymorphism. You entirely exclude the low-affinity binders from the study because they are unimageable. And for the remaining subjects, you must strictly control for whether they are HABs or MBABs in your final statistical models. If you compare a depressed HA to a healthy MA without correcting for the genetics, your data is complete meaningless fiction.
Wow. Once they figured out that genetic workaround, what did they actually find clinically? Does neuroinflammation play a role in psychiatry?
They found profoundly compelling differences. In major depressive disorder, multiple well-controlled studies have now shown a significantly elevated TSPO binding throughout the prefrontal cortex and anterior cingulate, heavily supporting the growing hypothesis that a distinct subset of depression is driven by, or at least involves, active neuroinflammation and microglial activation.
What about other disorders historically linked to stress, like PTSD? You would assume that severe trauma-induced stress would also drive up inflammation.
And that was the universal operating hypothesis. But a major recent study found the exact shocking opposite. Patients with chronic PTSD showed significantly lowered TSPO binding in prefrontal limbic regions compared to trauma-exposed healthy controls. And furthermore, this lowered brain signal correlated with lower systemic inflammatory markers in their blood, like C-reactive protein.
Wait, let's pause and think about the implication of that. The immune system in PTSD is suppressed, not hyperactive.
That is precisely what the in vivo data suggests. It implies that while we clinically group major depression and PTSD together broadly as stress-related disorders, their underlying neuroimmune pathophysiology may be entirely fundamentally divergent. It breaks our understanding of stress disorders as a single biological category.
Okay, this brings us to Section 5, Integration in Clinical Reasoning. We have spent an hour swimming in incredibly dense, fascinating research data. But if I am a clinical psychiatrist listening to this, how does this vast array of knowledge actually change the way I prescribe medication or think about treating the patient sitting in front of me?
The most direct, practically unassailable contribution of radiotracer imaging to daily clinical psychiatry is the concept of target engagement, quantified through receptor occupancy studies. Before the advent of PT, when a pharmaceutical company developed a new antipsychotic, figuring out the correct clinical dose was essentially a clinical guessing game. They gave the drug to patients and slowly increased the dose until the psychosis resolved or until the side effects became so utterly intolerable that the patient had to stop.
It was trial and error on human beings. But PT lets you look inside the brain and see exactly how many receptors the drug is actually blocking at a specific milligram dose.
Precisely. Let's look at standard first-generation antagonist antipsychotics like haloperidol, or even second-generation ones like risperidone. Extensive PET studies using tracers like 11C-raclopride demonstrated definitively that for these drugs to achieve clinical efficacy, to actually reduce the delusions and hallucinations, they must occupy between 70% and 80% of the striatal D2 receptors.
That is a very specific window. So is 80% the magic ceiling? What happens if you give a higher dose and hit 85%?
80% is the absolute neurochemical threshold for toxicity. The imaging confirmed that once D2 receptor occupancy crosses that 80% mark, the patient almost invariably begins to develop extrapyramidal symptoms, EPS. These are the devastating movement disorders, severe tremors, muscular rigidity, akathisia, and Parkinsonian side effects.
So the therapeutic window is terrifyingly tight. You need 70% occupancy to fix a psychosis, but if you hit 81%, you induce a crippling movement disorder.
Yes. This imaging data completely revolutionized how clinical trials design dosing schedules. It provided a hard biochemical rationale for seeking the absolute minimum effective dose.
But what about the atypical antipsychotics that break those rules? Clozapine is famous for being incredibly effective for treatment-resistant schizophrenia, yet it very rarely causes EPS.
NP imaging explained exactly why. Scans showed that clozapine produces robust clinical efficacy while only occupying roughly 50% to 60% of the D2 receptors. It operates on a completely different neurochemical paradigm, relying heavily on concurrent blockade of serotonin 5-HT2A receptors and featuring a very rapid off rate. It binds to the D2 receptor and then quickly dissociates, allowing natural dopamine to occasionally slip in and maintain normal motor function.
And what about a newer drug like aripiprazole?
Aripiprazole is fascinating from a pharmacokinetic perspective. It is a partial agonist, not a full antagonist. Because it stimulates the D2 receptor slightly while simultaneously blocking endogenous dopamine from binding fully, PET studies show it can safely occupy up to 90% or even 95% of the D2 receptors without triggering massive EPS. The intrinsic partial activity of the drug maintains just enough baseline dopamine signaling to prevent the movement disorder, while still dampening the hyperactive surges that cause psychosis.
Do we have these kinds of hard mathematical occupancy rules for depression medications as well?
We do. Imaging with SERT tracers like 11C-DASB has shown that for an SSRI like fluoxetine or sertraline to be clinically effective in treating depression, it requires 80% or greater occupancy of the serotonin transporter. This gives modern drug developers a clear mathematical benchmark. If an experimental new antidepressant only occupies 40% of SERT at its maximum tolerated dose, the company knows immediately that they likely need to abandon the compound. It will fail in phase 3 trials.
Give me a specific narrative example of how imaging directly solved a clinical trial mystery. The textbook tells the Pindalol story, and I think it perfectly encapsulates the power of PP.
The Pindalol story is a classic example of radiotracer imaging saving a theory from premature death. As we know, SSRIs have a notoriously long latency period. It takes weeks, sometimes 4 to 6 weeks, for them to start alleviating depressive symptoms.
Which is agonizing. If a patient is severely depressed, barely functioning, and you prescribe a medication, having to tell them this might not work for a month, hang in there, is clinically terrifying.
It is a major clinical failure. The prevailing biological theory for this delay focused on those 5-HT1A autoreceptors we discussed earlier. The theory was that when the SSRI initially blocks reuptake, serotonin pools in the synapse, but it also pools around the Raphi nuclei in the brainstem, heavily triggering those 5-HT1A autoreceptors, which immediately yell at the neuron to stop firing. So the system hits the brakes. It takes weeks of constant SSRI exposure for those autoreceptors to finally desensitize, burn out, and stop working, which finally allows the neuron to fire fully and the antidepressant effect to take hold.
So researchers thought, what if we just manually block the autoreceptor from day one, cutting the brakes entirely?
Precisely. They looked for an existing drug that could block 5-HT1A receptors. Pindolol, an older beta blocker used for hypertension, is also known to be a weak partial agonist at the 5-HT1A receptor. Clinicians excitedly started running major trials, co-administering Pindolol alongside standard SSRIs, hoping to completely skip the latency period and achieve rapid remission.
Did the trials work?
The clinical trials were a chaotic mess. A few showed slight benefit, but many failed completely to separate from placebo. The psychiatric field was devastated and was preparing to abandon the autoreceptor theory altogether. They assumed the fundamental biological premise was simply wrong.
Enter the PT scanner.
Enter 11C-Way100635 imaging. A group of researchers brought in healthy volunteers, gave them the exact clinical doses of Pindolol that were used in those failed trials, usually around 7.5 milligrams, and put them in the PD scanner. They found that at those specific doses, Pindolol was only occupying roughly 20% to 30% of the 5-HT1A autoreceptor.
It wasn't enough drug. They weren't actually blocking the brakes.
Exactly. The underlying neurobiological theory of depression wasn't necessarily wrong. The pharmacological dosing in the trials was simply utterly insufficient to achieve meaningful target engagement. And unfortunately, they couldn't just massively increase the dose of Pindolol to hit 80% occupancy because its primary action as a beta blocker would cause dangerous, life-threatening drops in blood pressure and heart rate. But the imaging proved definitively that the failure of the clinical trials was a pharmacokinetic failure of the drug, not a conceptual failure of the disease theory.
So, synthesizing everything we've covered today, if I am a clinician listening to this, I cannot just order a PT scan for my depressed patient tomorrow to see if their SSRI is hitting 80% occupancy.
No, you cannot. And that is the crucial grounding takeaway. Radiotracer imaging in psychiatry is primarily and almost exclusively a research tool, not a routine diagnostic one. The biological variability between individuals is too high, the overlap between healthy and diseased states is too broad, and the logistics of cyclotrons and short half-lives are far too complex for routine clinical diagnostic use. What this technology does is translate symptomatic psychiatry into neurochemical psychiatry. It ensures that the millions of prescriptions written every day are actually hitting the targets we think they are hitting. It provides the mechanistic, molecular foundation upon which all modern psychopharmacology rests.
This has been an absolutely staggering journey through the molecular machinery of the brain. To wrap up, we're going to move into our learning reinforcement segment. We have 6 single best answer questions to test your mental models of what we just discussed. I will read the question for you, the listener. Our expert will give you a moment to pause and think, and then deeply break down the correct answer. Question 1, concept. Which imaging modality utilizes the principle of coincidence detection to locate a radioactive decay event?
Take a moment to think about the physics we covered.
Okay.
The answer is PET, positron emission tomography. This entirely relies on the quantum physics of positron electron annihilation, which guarantees the emission of 2 511 keV photons in roughly 180-degree opposite directions. SPECT, in contrast, it detects single random photons using physical lead collimation.
Question 2, concept. In the mathematical two-tissue compartment model, what exactly does the parameter BPND represent?
Pause to consider the stadium parking lot analogy.
The cars and the VIP spots.
Yes. The answer is the ratio of specifically bound tracer to non-displaceable tracer at equilibrium. Mathematically, it is CS divided by CND. Physiologically, it represents a clean signal-to-noise ratio that is directly and linearly proportional to the available target receptor density, which we call B-veil.
Question 3, mechanism. Why do researchers use the amphetamine challenge protocol in 11C raclopride PET studies of schizophrenia?
Think about the presynaptic mechanism we discussed with the dopamine flood.
Right.
The answer is to induce massive endogenous dopamine release. Amphetamine forces the terminals to dump dopamine into the synapse. This endogenous dopamine competes with and displaces the radiotracer, allowing researchers to calculate the resulting drop in binding potential, which serves as a direct proxy metric for presynaptic dopamine release capacity.
Question 4, mechanism. What is the physiological limitation of using 18-FTG to measure cerebral glucose metabolism?
Consider the trap tracer model and the Roche motel concept.
Checking in but not checking out.
Exactly. The answer is it acts as an irreversible tracer. Unlike normal, natural glucose, which goes all the way through the metabolic cycle to produce ATP, 18-FTG gets phosphorylated by hexokinase but cannot structurally undergo further metabolic steps. It becomes permanently trapped in the cell, which allows us to mathematically measure the uptake rate constant, kin, but requires a specific mathematical conversion factor, the lumped constant, to approximate true glucose metabolism.
Question 5, clinical reasoning. Based on extensive key target engagement studies, what is the generally accepted D2 receptor occupancy threshold, above which extrapyramidal symptoms are highly likely to occur with standard antagonist antipsychotics?
Recall the narrow therapeutic window we just talked about.
Okay, what is it?
The answer is approximately 80%. Antipsychotics typically require 70% to 80% occupancy for clinical efficacy in treating positive symptoms. But crossing the 80% threshold drastically increases the risk of debilitating movement disorders.
Question 6, clinical reasoning. In TSPO imaging for neuroinflammation, why is mandatory genetic pre-screening required for second-generation tracers like 11C-PBR28?
Think about the patient variables and the binding site lock.
Changing locks.
Yes, the answer is due to a specific single nucleotide polymorphism, RS6971. This genetic mutation physically alters the binding site of the protein, creating high, mixed, and low affinity binders in the general human population. If you do not genetically screen and statistically control for this, the vast variance in specific binding affinity wildly and completely skews any quantitative results comparing patient groups.
Excellent. We have mapped the quantum physics, the mathematical models, and the stark clinical reality. Before we sign off, leave us with a final thought to ponder.
If we take a step back and connect all of this to the bigger picture, consider this limitation. Currently, the brilliant tools of PET and SPECT force us to look at the brain through a very narrow, highly specific keyhole. We look at dopamine over here in one study. We look at serotonin over there in a different study. We look at neuroinflammation in total isolation. But the human mind does not operate in independent silos. These systems interact continuously, intimately modulating and regulating one another. If a patient's mood, or their psychosis, is the result of a grand, complex symphony of neurochemistry, we are currently only capable of listening to the brass section, or only the strings. The true future of psychiatric imaging lies in understanding the complex, real-time intersection of these systems simultaneously. What happens to our diagnostic capabilities when our technology advances enough to hear the entire orchestra at once?
That is a profound place to leave it. Returning to our opening metaphor, we're getting incredibly good at tracking the GPS on a single fleet of vans, but eventually we need to understand the flow of the entire traffic grid. Here are the details of this episode. PSYCH 027, Radiotracer imaging with positron emission tomography and single photon emission computed tomography, fundamental principles, methodology, and role in neuropsychiatric research. Byline: tracking the invisible following molecules to understand function in the living brain.